Okay, related rates. As the name says, we're trying to find a relationship between two rates of change of two different quantities. Okay, so let's say imagine the situation that we're pumping air into a balloon. So I'm gonna make a drawing here. So I got this. Let's make it roughly spherical like this, and we're pumping air into it. And both the volume is increasing because more air is going in, right? And the radius of the balloon is also increasing. So both quantities are increasing. Both the volume and the radius are increasing, and these have to be related to each other because the more volume you need, the more radius you need, and vice versa, right? The more radius you have, that means you had more volume to make the balloon inflate. So there is a relationship between these two, and the related rates problem is to find the relationship between these two. Okay, that's what it is. Usually what we'll do is you find an equation that relates the two quantities, and that's step one usually, and that's where it gets hard, right? Because sometimes it's difficult to think of the equation or to remember the equation that relates the two quantities before differentiating, before finding the derivative, and then you use the chain rule to differentiate both sides. So that would be step two. That's usually how I go. And like I said before, this is a very short slideshow. As you can see, this is what makes it hard. It's very easy to explain through an example what you need to do, but then it's very hard to actually do it depending on the situation. So focus your time on coming to office hours and asking about examples and working on examples. Focus your time on understanding the procedure, and then if you're not able to find the equation, just come and ask me or someone else or a tutor or something. What's the equation for this? Can you explain to me how you came up with this equation? And it's going to work out for you okay. As the class progresses too, we're going to be using the same equations over and over, so it's not that bad. So let's say this example here. Air is being pumped to the balloon, so it's spherical balloon, right? They told us that it was spherical this time around. The volume increases at a rate of 1,000 cubic centimeters, so 100 cubic centimeters per second. So that's the amount of air going in, which is how the volume grows, right? It's the amount of air. How fast is the radius of the balloon? There's pressure issues, but don't worry about that. But how fast is the radius of the balloon increasing when the diameter? Okay, the diameter is 50. How fast is it increasing when the diameter is 50? So here's what I'll do. So first, the rate of increase of the volume is 100. I know that. And the unknown is the rate of increase of the radius, which is dr dt. I know that, which is dv dt. I'll call v the volume. And then the diameter is 50. So d is 50. Remember that the diameter on a sphere is the whole thing, which is twice the radius. So the radius is half of this, which is 25. The radius is 25, excuse me. Fix that real quick. Okay. Alright, so we got that. Let's answer the question now. First, I have to find an equation that connects both V and R, and that's the problem, like I said. That's the most difficult thing to do. So the volume of a sphere, and just the formula that I remember, is 4/3 of pi r cubed. It's not that difficult to remember. Pi's gotta go there whenever you're dealing with circles and spheres. Pi has to show up. Cubed because volume, right? Dimension 3. And then you only have to remember the 4/3. Okay, so it's not that bad. Okay, but that's the volume of a sphere. So that's step one, finding the equation that connects volume and radius. And now you differentiate both sides, so you gotta go dv dt, and now use the chain rule, because you can pull all the constants out. Pi is a constant. So you go by the chain rule, that equals to 4/3 of pi. Power rule first, 3 times r squared dr dt. Cancel the 3's. So you end up with dv dt equal to 4 pi r squared dr dt. So this is half the problem. The end now is just plugging in the known quantities to find what this is. Okay, to find out how fast the radius is increasing. Let me tell you this cool thing first. This here is the area formula for a sphere. Not that it's going to make a difference in this problem, but it has to do with the fact that to calculate the volume of a sphere, you can sort of add one sphere on top of another, on top of another, on top of another, with very, very thin spheres, right? If you put a sphere one inside the other, that's how you build the volume. That's something that you're going to learn in Calculus 3, if you go there, if you're interested in going that far into math. So I'll just erase this, but this is funny to notice. It's going to make a lot of sense as we go through, right? The volume is nothing like a bunch of areas put together. That's the idea, right? Just like if you think boxes, right? How do I calculate the volume of a box? What's the idea behind it? I can think about putting very thin, layers one on top of the other. Each layer has basically only area, but when I put them all together, then I get the volume, and that's the idea. Anyway, that has nothing to do with this problem. To solve this problem now, they're asking, well, how fast is the radius of the balloon increasing when the diameter is 50? So r is 25, so 4 pi times 25 squared. That's what I want to know, dr dt, because how fast is the radius increasing is the question. And the volume increases at a rate of 100, so dv dt is 100. So all I got to do now is solve for this. Yeah, so dr dt is 100 divided by 4 pi 25 squared. So that's it. I just plug that into my calculator and find out how fast the radius is increasing. So I'll do that just so I can give you a number. So that will be 100 divided by 4 pi times 625, right? 25 squared. See if my math went out okay. It does look good. So that's approximately 0.0. Does it say how many decimals it wants? Does not say. I like to use 3 decimals when they don't say, or I go with some other thing, some other estimate on my own. Like in the previous video when we're working with millions, I wanted to put like 4 decimals because 3 were given to me. But anyway, here nothing's given, so I'll just put 3. Let's say 0.1. Let's say 0.127 approximately, and that's radius. So radius is a length, right? So that's centimeters per second. So that's how fast the radius is increasing at that time. So again, my estimate is that, okay, as at that moment, in 1 second, I can expect that the radius is going to increase by roughly that amount of centimeters, right? 0.127 centimeters. So that's all we're doing. That's all related rates is about. And like I said before, this here is where the difficulty lies. Differentiating that is just about getting the hang of the rules that we already know. So this is where the difficulty lies for the various problems we're going to solve together. So I'll stop here. And the most important thing for you now is to practice this. Practice, practice, practice. Okay? So good luck with that. Let me know if you have any issues.